Dear student, in today's lecture, we have to start new chapter from the syllabus of Standard 12 Physics, chapter number 2, Mechanical Properties of Fluid. In 11th standard, you already learned a chapter with the heading Mechanical Properties of Solid. From that chapter, let me revise some points. We discussed the behavior of solid under the action of force. Let's see the difference between solid, liquid and gas. You can see a table. The first column represents properties. So here second column for solid, then next is liquid and then gases. So when we are talking about the first property, property of mass, all the three solid, liquid and gases having a definite mass. So when we are talking about shape, the solid having definite shape, the shape is fixed, definite shape. But liquid don't have definite shape. They acquire the shape of the vessel in which we pour the liquid, or the shape of the container they acquire. Gases also acquire the shape of container. Volume, next property we discuss, volume. Solid having definite volume. Liquid also having definite volume, but gas indefinite. Or we can say that, so the gases volume is not definite. So whole, if we consider the gases in a particular room, we can fix in a small box also, small box by compressing it. Next one is compressibility. Solids compressibility for solid, they are not possible. We cannot compress solid. For liquid, it is almost negligible. Compressibility for the gases, they are highly compressible. Fluidity, solid not possible, liquid can flow. For gases, can flow means having fluidity. Rigidity, solids are highly rigid, liquid less rigid, gases are not rigid. Diffusion, so solid molecules diffuse slowly, liquid very fast, sorry, liquid fast and gases very fast. Space between the particle, solids are having a most closely packed structure, liquid less closely packed and gases least closely packed. Interparticular force, in solid it is very strongest, it is slightly uh, weaker than the solid in the liquid, and in gases it is negligible. Now basically here, fluid. Fluid means a substance that can flow. Substance that can flow is called as fluid. And everybody know that liquid and gases, they can flow. So they are collectively called as fluid. Fluid word doesn't restrict only with the liquid. So gases also flow. So fluid means gases also. Fluid either has no rigidity or its rigidity is very low. In our daily life, we often experience the pressure exerted by fluid at rest in motion. Viscosity, surface tension play a very important role in nature. We will try to understand such property in this chapter. Pressure, viscosity, surface tension, these are very important properties. These properties we have to learn in this chapter. Fluid. Basically, what is fluid? Fluid is any substance that can flow. Any substance that can flow is a fluid. A fluid is a substance that deforms continuously under the action of external force. Fluid is a phase of matter that includes liquid, gases, and plasma. An ideal fluid has the following properties. We discuss some properties of fluid. The first property is it is incompressible. Its density is constant. Second property is its flow is irrotational. Its flow is smooth. There are no turbulence in the flow. So we can say that its flow is irrotational. It is non-viscous. There is no internal friction in the flow. That is, fluid has no viscosity. Its flow is steady. Its flow is steady. Its velocity at each point is constant in time. So we can say that flow is steady. So this is the properties of ideal fluid. So you note this word ideal. So ideally we consider the fluid is incompressible, flow is irrotational, it is non-viscous, its flow is steady. These are the ideal properties of fluid. Now, difference between solid and fluid. It is important to understand the difference between solid and fluid. Now, let me see solid first. Solid can be subjected to shear stress and normal stress as shown in figure. Shear means shape. The word shear means shape. And solid can be subjected to shear stress. Stress related to shape is the shear stress. And in that, we are considering tangential force. So you can see here, when we apply some tangential force on the upper layer, it gets displaced to new position D dash C dash from DC. Fluid. Ideal fluid, on the other hand, can only be subjected to normal compressive stress. It is subjected to normal or compressive stress. Here, stress may be a normal or tangential, that you remember in case of solid. But in case of fluid, the stress is normal. Normal means perpendicular to the surface. You can see in the diagram also. Some differences between solid and fluid. Solid opposes the shear stress, stress related to change of shape. Fluid does not oppose shear stress. You know that fluid can take the shape of a vessel in which we pour it. So it does not oppose any shear stress. Deformations are reversible in solid. For example, if we bend the scale, means a metal scale within a limit and release it again it as it is. But in case of fluid, deformation are not reversible. That we remember. In solid, they require a certain initial stress before they deform and start flowing. But in fluid, no requirement of certain initial stress before they deform and start flowing. So this is the difference between solid and fluid. Properties of fluids. First property, they do not oppose deformation. They get permanently deformed. They have ability to flow. They have ability to take the shape of container. Fluid exhibits these properties because it cannot oppose a shear stress when in static equilibrium. Fluids at rest. The branch of physics which deals with the property of fluid at rest is called as hydrostatics, which deals with properties of fluid. In the next few sections, we will consider some of the properties of fluid at rest, such as pressure, surface tension, viscosity, etc. Now we start pressure. What is pressure first? Basically, pressure is a force per unit area. The normal force exerted by fluid at rest per unit surface area of contact is called pressure. You can see the formula of pressure. You can see the diagram. In that first diagram 2.4, fluid exert force on vertical surface. In the second diagram, fluid exert force on horizontal surface. And force per unit surface area is pressure. And you remember this force is normal to the surface. 1 Newton weight is about 100 gram mass if G is 10 meter per second square. You know that F is equal to mg. If we consider F is 1 Newton, then M is 100 gram means zero point 0.1 and G is 10. 0.1 into 10 is again 1. SI unit of pressure is Newton per meter square, and this Newton per meter square is equivalent to Pascal. So this is small p. Pascal. Pascal is the name of scientist. So when we are writing the full form of the unit, this P is small. And when we are writing the symbol, P is capital. Dimension of pressure is L raised to minus 1 M1 T minus 2. So dimension you get by solving this dimension of force, which is L1 M1 T minus 2 divided by area L2. After solving this, we get dimension is L minus 1 M1 T minus 2. Pressure is a scalar quantity. Other common units of measuring pressure of gas are bar, torr. These are the common units. 1 bar is equal to 10 raised to 5 Newton meter per meter square, or 10 raised to 5 Pascal. 1 torr, or a full form is torricelli. 1 torr is equal to 1 upon 760 atmosphere. Another unit, hectopascal. 1 hectopascal is equal to 100 Pascal. The next article we have to start, and it is pressure due to a liquid column. Now we consider a liquid column in a water. Let us calculate pressure exerted by this liquid column, which is in the form of cylinder, whose area is A. You can see this area is A. A is cross-sectional area of that cylinder. Rho is the density of fluid. H is height of imaginary cylinder. The liquid exerts a force which is its weight. Liquid exert a force which is equal to its weight, mg. So this is the force mg. Therefore, the pressure exerted by liquid column on the bottom of cylinder is, formula of the pressure is force per unit area. So force is mg, area is capital A. Now we know that density is equal to mass upon volume. So mass is the density into volume. So this is the volume and this is the density. We use this formula here. By using that, so volume of cylinder is area into height. And density we already defined here, it is rho. So we get mass is equal to A, means area multiplied by height multiplied by density. Now this we have to substitute in a formula of pressure. So we get this formula, and from this formula this A and A get cancelled. We get expression for pressure, H rho G. So this is expression for the pressure exerted by a liquid column. And this pressure depends on this height, density and acceleration due to gravity. You remember, pressure does not depend on area of imaginary cylinder. Area get cancelled. You can see here AA get cancelled. So pressure does not depends on the area of imaginary cylinder. This pressure is called as gauge pressure. This pressure is called as gauge pressure. Every instrument, pressure measuring instrument gives the pressure. That pressure is the gauge pressure that you remember. Next one is atmospheric pressure. Earth's atmosphere is made up of a fluid, namely air. It exerts a downward force due to its weight, similar to the previous article. As the liquid column exerts the force equal to the weight, similarly, the air column also exerts downward force due to its weight. The pressure due to this force is called atmospheric pressure. Remember here, pressure due to this force is called atmospheric pressure. Thus, at any point, atmospheric pressure is the weight of a column of air of unit cross section from that point and extending to the top of the atmosphere. So at that point, pressure is force per unit cross sectional area, and that force is the weight of the liquid column. Clearly, atmospheric pressure is highest at the surface of the earth. It is highest at the surface of earth. The atmospheric pressure at sea level is called as normal atmospheric pressure. You remember this word. Normal atmospheric pressure means pressure at sea level. The density of air in the atmosphere decreases with increase in height. Increase in height, this density decreases and become negligible beyond height 8 kilometers. So we know that one formula, pressure is equal to H rho G. Pressure depends on density. As density decreases with increase in height, it means that density decreases means pressure also decreases. So that you can see here, height of the column producing atmospheric pressure at sea level can be taken to 8 kilometers. Okay. Beyond this 8 kilometer, so this density is negligible. So that height of air column producing atmospheric pressure at sea level can be taken to be 8 kilometers. Perfect or absolute vacuum is when no matter, no atoms, no or molecules present, means the vacuum. Now next article is absolute pressure and gauge pressure. Consider a tank filled with water as shown in figure. So this is a tank filled with water. Assume an imaginary cylinder of horizontal base area A and height x1 minus x2. The vertical forces acting on cylinder are: first force F1, which is acting downward at the top surface of cylinder. You can see here this is F1, which is in downward direction. F2, you can see here F2, acts upward at the bottom surface of the cylinder. You can see the direction of F2 in a diagram. Third force, gravitational force on the water enclosed in the cylinder is mg. This gravitational force equal to weight mg. In static equilibrium, we can write total upward force and total downward force. Both are same. F, you can write here in equilibrium, F upward is equal to F downward. Means total upward and downward forces are same. So upward force you can see in a diagram F2, and downward this weight and this F1. So F1 plus mg we get as a downward force. So this F1 we can write P1A, and F2 we can write P2A. We know the formula of pressure. P is equal to F by A. So by using that, F is equal to P into A. This is the formula that we use here. So F1 is equal to P1A and F2 is P2A. We are not using A1, A2 because we consider this imaginary cylinder whose area is fixed. Also, M is mass, and that mass we can write density into volume. So density rho, volume V, and that volume we can write area multiplied by height, and height is x1 minus x2. So we get mass is equal to density area into height, means x1 minus x2. Now we get in a formula F2 is equal to F1 plus mg. After substituting F2, F1 and m, we get this equation. So here A is common everywhere. We cancel A. This A get cancelled. So we get formula P2 is equal to P1 plus rho G in a bracket x1 minus x2. Now same formula we are writing in different way. Pressure at depth h below the surface of liquid. Now see here. So this top portion of this imaginary cylinder we consider on the surface in the previous diagram. So this cylinder is well inside the liquid. Now here it is on the surface. So we know the previous equation P2 is equal to P1 plus rho g x1 minus x2. Now let P0 is the atmospheric pressure at the surface. P0 is atmospheric pressure at the surface, means at x1. By substituting here, so we can substitute x1 is equal to 0 and this pressure 1 is equal to atmospheric pressure. So x2 is equal to, we can write minus h. P2 is equal to P. P means the pressure. So after substituting this in equation 2.6, we get P is equal to P0 plus H rho g. So we get this formula. P is equal to P0 plus H rho g. The above equation gives the total pressure or the absolute pressure. So this P is called as total pressure. So this formula we can write like this. So total pressure is equal to P0 is what? Atmospheric pressure. And this H rho g is called as gauge pressure. So we get formula here. Total pressure is equal to atmospheric pressure plus gauge pressure. In general, the difference between absolute pressure and atmospheric pressure is called as gauge pressure. So I told you H rho g is gauge pressure. So P minus P0, total pressure minus atmospheric pressure is the gauge pressure. And you remember one thing. So all the pressure measuring devices measure gauge pressure. Means the instrument which measures the pressure of the tire measure the gauge pressure. It gives gauge pressure. A blood pressure measuring device also gives us gauge pressure. It does not give a total pressure, that you note. Similarly, one more case we can consider for the same article. If we consider this cylinder like this, liquid column, not a cylinder, imaginary liquid column, then we can write pressure by this formula.